He never marched with a rifle. He never stormed a beach. Yet, every American victory in the Pacific carried his fingerprints. While generals planned battles and admirals commanded fleets, one engineer built the very ground they fought on. Airfields carved from jungle, harbours blasted from coral, supply routes created from nothing but sand, sweat and steel. His name was Ben Moreell, the man who invented the Seabees, the Navy's combat engineers who built faster than the enemy could destroy. And without him, America's island-hopping strategy might never have worked. Moreell's rise did not begin on a battlefield. It began in the disciplined world of industrial engineering, where precision mattered more than rank. Born in 1892 to immigrant parents, he grew up in a country transforming itself through steel, railroads, and machinery. Engineering was not glamorous, but Moreell understood early that infrastructure shaped power more than speeches or headlines. After graduating from Purdue University, he joined the US Navy as a civil engineer, at a time when the Navy was expanding into one of the most advanced maritime forces in the world. He learned quickly: docks, dry docks, fuel depots, and ship repair facilities. These were the arteries of naval strength, and Moreell became one of the men who designed them. By the 1930s, the United States faced a brewing conflict across two oceans. Japan was expanding aggressively in the Pacific, while Germany's rearmament accelerated in Europe. The Navy's leadership needed engineers who could build under pressure, scale operations quickly, and understand the logistics of global warfare. Moreell stood out. His projects were delivered on time, often under difficult conditions, and he demonstrated an unusual ability to think several steps ahead. What would be needed, when and how fast it could realistically be built. In 1937, he was appointed Chief of the Navy's Bureau of Yards and Docks, making him responsible for nearly every construction program the Navy undertook. It was one of the most demanding engineering positions in the United States. Under his direction, the Navy expanded bases in Hawaii, the Philippines, in Alaska, and the Caribbean. He oversaw dry dock expansions that allowed America to maintain battleships and aircraft carriers thousands of miles from home. These projects were massive, but they were nothing compared to what was coming. When Japan attacked Pearl Harbor in December 1941, America faced an engineering crisis unlike anything in its history. The Pacific was not Europe. There were no rail lines, no highways, no deep water ports waiting to be captured. If the US wanted to fight island by island, it would have to build the war as it advanced. Bombed out coral reefs needed to become runways. Bare sand needed to become supply hubs. Remote islands needed to support thousands of troops within weeks, not months. And civilian construction teams, the people normally responsible for building bases, could not operate under fire. They had no training, no weapons, and no legal protection under the rules of war. When Japanese aircraft attacked Wake Island in 1941, several civilian contractors were killed or captured. Moreell realized immediately that America needed something entirely new: construction forces who could fight and build at the same time. So he created them. In early 1942, Moreell proposed the formation of a specialized naval construction unit composed of skilled builders, welders, electricians, mechanics, and engineers, all trained to defend themselves in combat. The idea was radical. No navy in the world had anything like it. Combat troops were not builders, and builders were not combat troops. But Moreell insisted. The war required a hybrid force, and only the Navy had the logistics to support it. The Navy approved his request, and the construction battalions were born. Their nickname came naturally, the Seabees. Moreell designed their mission, their structure, even their culture. They were expected to build under fire, repair under threat, and improvise solutions with unmatched speed. Their motto captured the entire philosophy: we build, we fight. Training was fast and intense. The men learned how to use heavy machinery and weapons in the same week. They memorized field construction methods, practiced rapid runway repairs, and trained to defend themselves against ground attacks. Moreell set the standard: toughness, creativity, precision. Within months, the Seabees were deployed across the Pacific. What they built next would shape the entire course of the war. But before the Seabees landed on their first contested beach, one question defined the challenge ahead. Could a force of engineers truly keep pace with the fastest-moving war the United States had ever faced? The first test of Ben Moreell's new engineering force came almost immediately. The Pacific campaign demanded speed, and every hour lost on an unfinished airfield or an unusable port meant delayed operations and increased casualties. The Seabees were thrown into conditions that would have broken conventional construction units. Their first assignments were not practice runs. They were frontline engineering challenges in environments shaped by heat, coral, jungle, and relentless enemy pressure. One of the earliest critical tasks was the reconstruction of facilities damaged during the opening months of the war. At Pearl Harbor, repair crews worked around shattered infrastructure, twisted steel, and fuel depots still burning from the attack. Moreell directed resources with urgency, prioritizing dry docks and repair stations that could return warships to service. Within weeks, ships that should have taken months to fix were back at sea. It was an early demonstration of what would become the defining feature of Moreell's strategy: industrial-scale engineering carried out at operational speed. As US forces prepared to push west across the Pacific, the importance of rapid construction became even more clear. The geography offered no shortcuts. Operations could not depend on existing infrastructure. Every island targeted for invasion lacked the essential facilities needed for sustained conflict. For Moreell and the Seabees, this meant that success depended on creating order from untouched terrain. Coral needed to become pavement. Marshland needed to become foundations. Narrow beaches needed to become supply arteries. At Guadalcanal, early operations revealed the scale of the challenge. Many landing zones were unstable, and construction materials were limited. Seabees arrived under threat of attack, carrying equipment across beaches still contested by Japanese forces. Working under fire, they graded runways, reinforced embankments, and established defensive positions, while simultaneously building the infrastructure needed to keep aircraft operational. Their ability to shift instantly between combat and engineering became the signature of Moreell's concept, a dual-role force capable of functioning where civilian crews could not. As operations expanded, the engineering problems grew more complex. At Espiritu Santo, Seabees converted dense jungle into a massive naval base. They blasted through coral, drained swamps, and erected fuel depots large enough to supply multiple task forces. The site became one of the most important logistical hubs in the Pacific, supporting operations from Guadalcanal to the Central Pacific. Moreell monitored progress closely, reviewing reports that detailed equipment use, material shortages, and project timelines. His leadership kept construction aligned with tactical needs, ensuring that infrastructure remained synchronized with operational momentum. The strategic shift toward the Central Pacific introduced even greater obstacles. Islands such as Tarawa, Makin, and Kwajalein were small, exposed, and surrounded by reefs that disrupted landings. These operations demanded precise coordination. Seabees followed assault troops ashore, clearing obstacles and constructing beachheads, while enemy resistance continued. On several islands, they built airfields within days of securing territory. This accelerated pace allowed American aircraft to protect supply lines and strike deeper into Japanese-held territory. Moreell's engineering philosophy emphasized adaptability. Every island presented a different geological and environmental profile. Traditional methods could not be applied uniformly. Coral runways required crushing and layering techniques that differed from a volcanic terrain. Harbours carved from reefs demanded explosives, dredging equipment, and reinforced breakwaters. Moreell pushed for innovation, encouraging officers to experiment with new construction methods and share solutions across units. This decentralized problem-solving culture allowed engineering teams to overcome logistical challenges without waiting for lengthy directives. The turning point came with the operations at Saipan, Tinian, and Guam. These islands needed to support long-range bombers that would eventually reach Japan. Their runways had to be exceptionally strong, long, and resistant to heavy operational stress. Seabees cleared tens of thousands of tons of rock, built expansive road networks, and erected warehouses, hospitals, and repair centres at unprecedented speed. Tinian became one of the most advanced air bases in military history, eventually serving as the launch site for B-29 operations that shifted the strategic balance of the war. Throughout these massive construction efforts, Moreell managed the broader vision from Washington. He monitored supply chains, secured equipment, and ensured that manpower was distributed effectively across theatres. His ability to translate operational requirements into bore engineering priorities kept the Pacific advance synchronized. Every decision reinforced a singular objective: to maintain continuous forward momentum. The Seabees could not afford delays, and under Moreell's leadership, they rarely experienced them. This period demonstrated the full impact of Moreell's innovations. Engineering was no longer a background function. It had become a central component of strategy. Every airfield shortened the distance to the next objective. Every harbour increased the speed of resupply. Every road and storage depot improved operational endurance. Moreell had redefined the relationship between engineering and warfare by proving that infrastructure built at combat speed could determine victory across entire theatres. Yet, even as the Seabees succeeded across the Pacific, a larger question emerged. The war was moving toward its most challenging phase. The next islands would be larger, more fortified, and more strategically essential. Engineering demands would reach their highest point. Could Moreell's vision scale to meet the final, most demanding operations of the Pacific War? By 1944, the Pacific Campaign had entered a phase where every operation required engineering on a scale unmatched in military history. Amphibious landings were no longer isolated events. They were sequences of interconnected offensives that depended on continuous infrastructure stretching thousands of miles across ocean, reef, and volcanic terrain. For Ben Moreell, this meant that the Seabees could no longer function as a series of individual units. They had to operate as a coordinated engineering network capable of reshaping entire regions at operational speed. The first test of this new scale emerged during the invasion of the Marshall Islands. At Kwajalein, Seabees faced coral terrain so hard that conventional arranged construction methods proved ineffective. Bulldozers shattered blades against it. Picks and shovels barely scratched the surface. Instead of halting progress, teams adapted by blasting coral layers, screening the fragments, and repacking them to create stable foundations. The process transformed material that had resisted them into the runway surface itself. Moreell viewed this adaptability as proof that the Seabees had evolved beyond the limits of standard field engineering. They were now capable of inventing solutions specific to each battlefield. At Eniwetok, another challenge emerged. The islands were small, exposed, and vulnerable to shifting tides. Construction crews built seawalls, deepened channels, and installed fuel storage facilities in areas where storms threatened to undo their work. These efforts created logistical hubs capable of supporting naval task forces pushing deeper into the Central Pacific. Moreell understood that every gallon of fuel stored, every metre of runway poured, and every pier reinforced increased the operational endurance of the fleet. Engineering was becoming a force multiplier at the strategic level. As the war moved toward the Marianas, the stakes rose dramatically. Saipan, Tinian, and Guam were essential for the next stage of American strategy. They offered the range needed for long-distance bombing operations, and their infrastructure had to support aircraft unlike any used earlier in the war. The B-29 superfortress required runways far longer and stronger than those built on previous islands. Completing these airfields demanded a scale of labour that pushed the limits of speed and endurance. On Saipan, Seabees worked through extreme heat and terrain carved from volcanic rock. They blasted ridgelines, filled ravines, and designed drainage systems capable of handling sudden tropical storms. The result was an airfield complex that stabilised American air operations in the region. But Tinian represented an even more ambitious undertaking. The island's terrain offered a rare advantage: long, flat limestone terraces ideal for large-scale airfield construction. Moreell recognised the opportunity immediately. Under his guidance, Seabees built two massive airfields, Northfield and Westfield, each capable of supporting hundreds of B-29s. These installations became the operational heart of the strategic bombing campaign, proving that engineering decisions could influence outcomes at the highest level. Material shortages complicated every step. Steel, heavy machinery, concrete, and fuel were all limited resources. Moreell solved these constraints by implementing an engineering logistics model tailored to wartime conditions. He coordinated supply chains across multiple naval districts, redirected shipping priorities, and synchronized deliveries with projected construction timelines. This system ensured that CB units rarely stalled for lack of material. Their ability to maintain momentum became one of the defining elements of the Pacific Advance. Beyond construction, Moreell faced the problem of defending the infrastructure once built. Airfields, harbours, and supply depots were immediate targets. Seabees installed protective revetments, repaired runways under fire, and maintained essential facilities, even as enemy aircraft attempted to disable them. Their dual role as builders and fighters, envisioned from the very beginning, now proved essential. On multiple islands, they restored critical structures within hours of attacks, allowing aircraft to resume operations without significant delay. As the front moved closer to Japan, the demands intensified again. At Iwo Jima, volcanic ash consumed equipment, clogged engines, and made grading nearly impossible. Yet, within days of securing the island, Seabees carved out runways that allowed damaged B-29s to make emergency landings on their return routes from Japan. Thousands of airmen owed their survival to these improvised facilities. For Moreell, these landings represented the purpose of the entire CB program. Engineering used not as background support, but as a decisive factor saving lives and maintaining strategic tempo. Okinawa, the final major offensive of the Pacific, presented the most complex engineering challenge of the war. Torrential rains, mud, and constant artillery fire tested every construction plan. Seabees built roads that held under heavy armour traffic, repaired airfields repeatedly, and created supply lines capable of supporting the largest amphibious force of the conflict. Moreell monitored these operations with the understanding that success required absolute coordination between engineering and combat units. The scale of construction on Okinawa demonstrated how far the program had evolved since its inception. What had begun as an unconventional idea had become one of the most capable engineering forces ever assembled. By the middle of 1945, the role of engineering in the Pacific War was no longer theoretical. It shaped strategy, dictated timelines, and determined what operations were possible. Moreell's concept had changed the nature of military infrastructure, turning it from a long-term planning exercise into a frontline capability built in real time. But as the war neared its conclusion, a new challenge appeared on the horizon. The Seabees had proven themselves indispensable in combat. The question now was whether their capabilities could adapt to the demands of a world transitioning toward the final phase of the war, and the uncertain peace that would follow. Could Moreell's engineering force influence the outcome of the closing operations and shape the post-war military world they were about to enter? As 1945 approached its violent conclusion, the Pacific Campaign entered a phase where engineering dictated not only the pace of operations, but the shape of the final assault on Japan. For Ben Moreell, the war had become a demonstration of how infrastructure built under fire could shift the balance of global strategy. Yet, even as the Seabees continued carving runways from volcanic ash and transforming shattered coastlines into functional harbours, Moreell had begun preparing for a challenge that extended beyond the current conflict. The end of the war would not diminish the need for rapid, adaptable construction forces. In many ways, it would amplify it. The first indication of this shift came with the unprecedented build-up required for Operation Downfall, the planned invasion of the Japanese home islands. Although the operation was never executed, the engineering preparations were enormous. Moreell oversaw a vast expansion of construction capacity, including logistics hubs, supply chains, and specialized units trained for rapid deployment in contested terrain. These preparations demonstrated how far the Seabees had come since their improvised beginnings. They were no longer a wartime experiment. They were a permanent, highly coordinated engineering arm with global responsibilities. Even after the atomic bombings ended the war before an invasion occurred, the scale of reconstruction and occupation demands revealed the importance of maintaining this capability. In the immediate aftermath of Japan's surrender, Seabee units shifted seamlessly from combat engineering to rebuilding essential infrastructure. Airfields were repaired, ports restored, and transportation networks stabilized to support humanitarian aid, military administration, and the transition to peacetime governance. Moreell recognized that engineering forces trained under combat conditions were uniquely prepared to handle the complex blend of urgency and precision required during occupation. The broader military establishment began to acknowledge what Moreell had understood from the start. Engineering was a strategic instrument, not merely a support function. His advocacy ensured that the Seabees remained part of the post-war US Navy, with formal recognition of their engineering capabilities and their role in future operations. Under his guidance, training programs expanded to incorporate lessons learned across the Pacific. New equipment, doctrine, and organization structures emerged as the Navy prepared for a world where infrastructure had become a decisive element of military power. As the United States entered the early years of the Cold War, the need for rapid construction forces only grew. Strategic airfields, radar stations, fuel depots, and naval bases had to be built across remote regions. Moreell's influence was clearly visible in these efforts. The engineering philosophy he established prioritized speed without sacrificing durability, adaptability without compromising, structural integrity. His emphasis on modular construction, decentralized logistics, and broad technical training allowed Seabee units to operate effectively across climates ranging from Arctic stations to tropical bases. Moreell himself transitioned into new leadership roles that extended beyond direct engineering oversight. As an admiral, he advised on infrastructure programs central to national security, including base construction, fleet support facilities, and global supply networks. His expertise ensured that engineering remained integrated into broader strategic planning. He had become not just the founder of a wartime force, but an architect of the United States Navy's long-term logistical framework. The civilian world also felt the impact of his wartime innovations. Techniques pioneered by the Seabees, prefabricated structures, rapid runway construction, flexible port facilities, and modular transportation systems, and he influenced post-war engineering and reconstruction projects globally. Nations recovering from the devastation of war adopted methods refined under Moreell's direction. His legacy extended into highways, industrial developments, and emergency infrastructure, far removed from the battlefields where the ideas first took shape. Throughout his career, Moreell remained defined by discipline, clarity, and an unwavering belief that engineering was a matter of responsibility rather than prestige. Colleagues noted his ability to reduce complex logistical challenges into structured, actionable problems. He never glorified his accomplishments or the organization he created. Instead, he emphasized measurable outcomes: runways completed, harbors opened, supply lines sustained, lives saved by timely construction. His leadership style set the tone for the entire Seabee community, a culture grounded in action, not rhetoric. By the time he retired, the Seabees had become a permanent institution, their reputation cemented by decades of performance. Their emblem, a construction bee carrying tools and weapons, reflected Moreell's original vision: builders capable of fighting when necessary, fighters capable of building when essential. They could move faster than conventional engineering units, maintain momentum under conditions that halted others, and deliver infrastructure where strategy demanded it, not where environmental conditions made it easy. Ben Moreell's work reshaped the relationship between engineering and warfare. He demonstrated that the ability to build was as decisive as the ability to destroy. Every airfield carved from coral, every port dredged from volcanic ash, every supply road laid under fire reinforced the principle that operational success depended on the precision, endurance, and innovation of engineers. As the world transitioned from global war to uneasy peace, Moreell's creation endured. The Seabees evolved with new technologies, new missions, and new geopolitical demands, yet their core identity remained unchanged, a force built on the belief that engineering, executed with clarity and discipline, could shape the outcome of conflicts and the stability of nations. With the Pacific War behind him and the Cold War beginning to take shape, one final question defined the legacy of Ben Moreell and the engineering force he brought into existence. How would the Seabees, forged under the pressure of total war, shape the military world that followed and the global challenges still to come?